It's my pleasure to introduce Paul Seidel from MIT, who's going to talk about the quantum connection, familiar yet puzzling.
Thank you very much for inviting me. I see that there is here on top, there is a copy of the Harvard College Honor Code, which says that plagiarizing or misrepresenting the ideas of someone else as one's own violates the standards of our community. And I suddenly realized that I might be a little bit in trouble, especially concerning the misrepresenting part. This is not my typical kind of talk. I've tried to sort of start things sort of from the other and most classical and most elementary end. But you know that involves, there are many small mistakes in this talk that I'm aware of, that I'm doing to simplify things. And then there are probably some rather larger mistakes that I'm not aware of, which are probably on the level of, you know, every 19th century mathematician would have known. Okay, so what am I talking about here? So take a closed symplectic manifold, and I will assume that the cohomology class of the symplectic form is also the first Chern class. So for algebraic geometers, you take a smooth Fano variety. And I will take the small, in fact, the very smallest quantum connection. Which is a linear differential equation. And it is this one here. But this thing, this star here, I should put in a Q, stands for the small quantum product. So when you expand it, it has the ordinary cup product, and then there's a term with the next higher order power of Q. Okay, and so this term here, this has degree 2. Right, the cup product with the symplectic form. This has degree 0. This is degree -2. And then for simple degree reasons, it will terminate after finitely many terms. And each of these terms is a very simple enumerative invariant, a genus 0 Gromov-Witten invariant of the very simplest kind. So what we can see right away is that you know, there's a pole, so at Q equals 0, there is a simple pole and a regular singular point. Okay, whose residue is this cup product with omega, which is a nilpotent operator and hence gives rise to unipotent monodromy around this. In fact, this is very well known. There is a, you know, the fundamental solution around 0 was given a geometric interpretation by Giventhal. What I'm actually interested in is the Q equals infinity structure. And this is subject to a lot of conjectures by you know, Dubrovin and Galkin and Iritani, which seem to be beyond our power to do anything about. In part because when you look at these conjectures, you see that in fact they are well defined, the fact that they make sense depends on another and simpler layer of conjectures, which we also have no idea how to prove. So, so I will stick to that very simple basic layer and see. So what could I possibly not know about this thing here? Okay, so let me show you what the structure Q equals infinity looks like in case you have not seen before. So if I change to another variable, so then it will look like this. So the, you know, d by dq is minus q squared d by dq, and then there is a q times. So now the formal variable here, instead of being q, is obviously q inverse. Or in other words, you just want to write it as a connection. Okay, so now this looks, maybe at this point here, I would like just write it as a connection in this variable q. This looks terrible because, here we have, start with a q inverse term, and then there will be higher and higher powers of q inverse. So it looks like it would have a very high order pole, but that's an artifact of how you've written it. Okay, so there's a thing about degrees. Okay, so if we rescale, this is something acting on the cohomology. So if I rescale this part here by q to the power k over 2, then the connection takes on the following form. So just change this base, do this thing here, and then the connection here looks like this. This is now where you took, instead of having a formal power, you just said inside here, you said bq equals to 1. So you just add up all those terms, or the classical one, the 1 and the 2 and so on, and just take their sums without any variable, and you multiply this with q to the minus 2, and then you, that comes from here, then you pick up another term from the differential. This is simply the operator that acts on the degree k cohomology by multiplying it with k over 2. Okay. So it's very simple. You have this quadratic pole, and then you have this simple pole here. So this is usually, it's a quadratic pole, but it's also usually not a regular singular point. Okay. So what is the simplest class of meromorphic connection beyond those that have a regular singular point? Okay, so if I assume, so this is a general definition, and it's done in the world of formal power series, and it's important to do this. So if I look at a connection here, so these are matrices that have Laurent series in Q, okay, is of unramified exponential type. It's formally equivalent to a direct sum of connections of the following form. So these are just complex numbers. They're just a multiple of the identity matrix. This is the quadratic pole, and plus terms of Q inverse and higher. Okay. So if if all the alpha i's are 0, that would be just saying that well, you've reduced the pole order to 1, which is a definition of a regular singular point. So this is a generalization where you allow a direct sum with different kind of alpha i's. The exponential type will be clear to you if you try to actually solve this equation, why that is the case. Okay, so this is unramified exponential type. Nope. Okay. Okay, so so remark. So these are formal, this is a world of formal power series. So in general, it's a bit of a question, what does it mean for a formal connection to have monodromy, given that you can't actually solve the equation? I mean, or rather, in which class of problems you can solve this? But for things that have just a simple pole, it's a well-known thing. In fact, formal solutions and actually convergent solutions are actually one-to-one correspondence and so on and so on. So we can subtract the alpha IQ minus 2 term. Look at the fundamental solution. Which is generally speaking multi-valued, and thereby define so for a connection which is of unramified exponential type, we can define monodromies by taking each piece and subtracting out the quadratic part. I call these things personally the regularized form of monodromies. Regularized meaning that you take out the irregular part with the q to the minus 2, and formal meaning that's really in the world of formal power series. Okay, so this is your background. Okay, and so the conjecture comes in two parts. One is quite well known. It's in the literature, is that the quantum connection is of unramified exponential type. At q equals infinity. So if you do a formal expansion in 1 over q, like I've done it there, then this is of unramified exponential type. And the second thing is the regularized formal monodromies. Monodromies are quasi-unipotent. Meaning eigenvalues are roots of unity. This is maybe not so, I have not found this in the literature. I hope it's not because it's wrong. Okay, so I don't think I have time to actually give an example, but there are, there's of course many cases where this is true. This is known, and it's in a sense a consequence of mirror symmetry under certain assumptions. Okay. So I will try to explain to you what people mean by a consequence of mirror symmetry, but obviously if you want to think about this stuff in general, at this point here, there's a sort of bifurcation in strategies. You can either say, well, this is really a statement, but it's not really a statement about Fano varieties. It's a statement about mirror symmetry, and it will only hold insofar as you understand mirror symmetry. I find this a bit annoying, but the other thing is, what can we say about this without having, recourse to the other side of the mirror correspondence? Okay. Any questions so far? Everyone's happy?
Are you going to tell us what the mirror problem is?
Yes, in just a second. I hope so. Okay. So I have to give you more background here. Okay, and that background will help you understand. By the way, I should say that, so of course, this is not trivial. So not every connection with a quadratic pole is of unramified exponential type. What happens is that sometimes this kind of decomposition doesn't exist. It only exists after passing to a root of the variable q, and it involves lowering the power of the pole from 2 to some fractional power. But on the other hand, if you write down a random thing with a quadratic pole, very likely it has unramified exponential type, which is a little frustrating. On the other hand, this quasi-unipotency of the monodromy would typically not be true if you wrote down something randomly. So this is maybe a more genuine test whether we understand things. Okay, so so the next piece of background is that I have to look at a bit of abstract theory of differential equations in its model form as a theory of D modules. Okay. So what I will not explain the adjective holonomic, it's some kind of finiteness condition. So, but a D module is a vector space with say an action of Q and an action of T. Commutator is the identity. Okay. And you can think of this in two ways. You can think of Q as really multiplication with a variable Q, and then you can think of T as differentiation in some Q direction, in which case I will write it like this. So then it looks like something which is a sort of generalization of a connection over Q, or since there's a symmetry here, or as Q equals minus a connection up to the side in T direction. So it's also a different connection in T direction. Those two things are necessary. So if you think of it over here, or you think of it over there, it's an algebraic form of the Fourier transform. So it's called the Fourier-Laplace transform. So I should say one thing about holonomic D modules. So D is holonomic. It's essentially, if you look at it, let's say in the T variable, then away from finitely many T values, it is actually a vector bundle with a connection. Okay, so it is a polynomial such that if I extend variables by removing the zeros of P, okay, is a, well, it's a vector bundle over a punctured plane, but an algebraic vector bundle, so it's a trivial vector bundle. Connection. And the points that you had, T points that you had to remove in order to make this happen are called the singularities of the D module. And so there are singularities in T direction and singularities in Q direction. Of course, their structure is, and well, where they lie in their structure is absolutely not the same. Okay. So So one of the basic theorems in this direction is due to Malgrange. Okay, again, V is a holonomic D module. Okay, so if, so now I think of it as a vector bundle with a connection here, has regular singular points. Singularities, let's call them, including at T equals infinity. So then The Fourier-Laplace transform, which is the same thing, so has a regular singularity at q equals 0 and unramified exponential type at q equals infinity. Okay, and the second part of this is if in addition has quasi-unipotent monodromy around each singularity in C. So the singularity at infinity is actually irrelevant here. So then these regularized formal monodromy. Formal monodromies. Have the same property. Okay. What happens here is that under this assumption of regularity at infinity, every singularity of nabla T, which is finite, contributes one of the direct summands in this formal decomposition of nabla Q. In fact, these alpha i's that I wrote down are the locations of the singularities here. And the monodromies are related not in a straightforward way because the ranks of the, ranks of the two vector bundles are actually not the same. But where they differ is essentially, has to do with eigenvalues 1, so we're not worried about that too much. Okay, so this gives us the strategy for thinking about this, right? So these properties that we have in Q are exactly the properties that we wanted the quantum connection to have. We wanted it to have, well, we know it has a regular singularity at 0. We wanted it to have unramified exponential type at infinity. And we wanted these regular formal monodromies to be quasi-unipotent. So what we have to find is we have to, ideally represent this as a Fourier-Laplace transform of something that has regular singularities everywhere and quasi-unipotent monodromy. And then we win. Okay. All right, there's a couple of wrinkles here. So, are there any questions now? You can ask me. So let me show you what the mirror picture actually looks like, and how once you have gone through mirror symmetry, it actually it implements this strategy here. I'm famous for my inability to remember which board is which. It should be simple because from left to right is from back to forward, but okay. So this is again classical, right? So the mirror of a Fano variety is, well, to be precise, at this point, you have to start putting in some geometric conditions. So you have to assume that your Fano variety has a smooth anticanonical divisor. And then the mirror, that will generate a mirror of the following form. So look at the Ginzburg theory of superpotential, and so X is a smooth divide variety. And W a proper map. Okay. And so first I need something which is sort of a connection in Q direction. Like this. So you take algebraic differential forms. with this differential, the usual Durham differential, and Q times wedge product with dW. Okay, this is a module. This carries multiplication with Q, with T. So this is a plus. Sorry. Just positive powers of Q with a T acting by so this is what makes this one here into a D module. In fact, it's a chain complex of D modules because there's a differential. So so when I say cohomology, I'm always taking hypercohomology. Okay. Yeah. So this is okay. So this one here. The holonomic D module. As I said, holonomicity is a sort of finite generation condition. Okay, so this follows from the degree filtration. So if you do filtrations by degrees, right, the differential here increases degrees, so you do filtrations by degrees. So okay. So, all right, you notice that here there's something slightly different, which is I didn't look what the quantum connection actually. So this is it's trying to be the mirror of the quantum connection. It's not exactly precise because I only have positive powers of Q. So let me introduce the negative powers of Q as well. And since I ultimately want to do a formal expansion around Q equals infinity, I will arrange the formalism so that this is actually built in. So look at meaning what? I allow infinitely many, so finitely many positive powers of Q and infinite power series in Q inverse, okay, with the same structure. And so this is a little bit different, right? So H star of E, if you look at the hypercohomology here is T torsion. It's concentrated finitely many values of T. Okay, why is that the case? I can actually explain this to you. Okay, so let's take a look at what this actually looks like. Maybe it's good to decrypt this a little bit, right? So I would have, say, just like these powers of Q. Okay, all right. And then, of course, you have the Durham differential here. And you have then Q times dW wedge, which goes like here. Okay, so the consequence of this is that there is a decreasing filtration, of which, not by degrees this time, but this would be one stage of the filtration. And the next lower stage would be this one here. So this is a complete decreasing filtration because of this infinite power series in Q inverse. Gives me a spectral sequence. Okay, computing the cohomology of E. And now starting from this thing where only dW has the differential. So, okay, so now this complex here of sheaves is a cyclic, except where W has critical points. And so the this is supported at the parts of X where W has critical points, so there are finitely many critical fibers. And moreover, okay, I'm sorry to say this. So this note, did I do something wrong here? I think that Q should be there, but anyway. Okay. All right, so on this graded quotient, on this quotients here, it acts by W. So when you look at this thing here as a modulo of C bracket T, it is supported at the values where W has singular fibers. Okay. So this is the positive and negative version of this one here. So finally, look at I think we have only negative powers here. So you could write it like this thing here, so that would be slightly inappropriate. Okay, so what does this actually look like? You can actually see what happens here. There, sorry, I should say this. This is Q times dW wedge. Okay, so when you take this E minus here, then you are truncating, right? So it will stop at Q inverse here. And you will see that the rightmost column is just differential forms from X divided by dW wedge, which if I forget about the critical points for a moment, that would be fiber-wise differential forms. W is the dt variable from the base, and you sort of divide out. Okay, so after removing something slightly sloppy, singular fibers, the Fourier-Laplace transform of H star E minus. Okay, this has to do with fiber-wise differential forms of this thing, and entirely unsurprisingly, what it is actually the Gauss-Manin connection. Meaning the connection on the Dubrovin cohomology of the fibers. Okay. All right. Now we actually, so this means this is true, the Gauss-Manin connection here. This is looking at T, and you use the differentiation is actually nabla T, which was our previous Q. Okay. This is the connection, Gauss-Manin connection. Okay, and now we get to Potty. Okay, so we have the monodromy theorem in algebraic geometry, which says that Gauss-Manin has regular singularities, including at infinity, and quasi-unipotent. This is a delta T. Okay, so now so the Gauss-Manin connection, I led you through this whole labyrinth here. So the Gauss-Manin connection is really this E minus thing. But the difference between, there's a long exact sequence of cohomology of E minus, E and E plus, and the E part is only concentrated at finitely many values of T. So if you remove those finitely many, then the cohomology of E minus and E plus becomes isomorphic. And so you can carry over this result from E minus to E plus. And then the Lagrange's theorem says that the Q connection has, you know, unramified exponential type, et cetera, et cetera. Okay. So what happens is that you write, so if you wanted to sort of apply mirror symmetry, so you sort of have some sort of mirror situation in mind, which is like this, okay? Then you use the algebraic geometry of the mirror situation in the form of the monodromy theorem, which is the key thing that makes things run. And then you carry it over to a statement on this one here, and then part of your proof of mirror symmetry is hopefully that, well, at least once you invert Q, that this one here is actually the quantum connection, okay? And of course, in many cases, when we, you know, when we have sort of classical mirror symmetry, it includes writing the quantum connection in this form for a particular superpotential. And so it is part of the, you know, standard theory of mirror symmetry, let's say for, you know, Fano toric varieties or something like this. Okay. Okay. Of course, now the fun starts, which is, you know, how about in general? Meaning, I start with a Fano variety. Okay, maybe I can make some simplifying assumptions, but I want to, you know, to dig into the structure of the quantum connection without proving mirror symmetry. After all, you know, there's a you know, whether mirror symmetry is actually true for all Fano varieties is, I believe, a matter of, you know, that is a very difficult question, in part because all known approaches involving, you know, certain degenerating the Fano varieties. So you're essentially saying that you believe that all smooth Fano varieties can be degenerate to certain singular limits. Seems a very bold move to me, but I'm not an algebraic geometer. Plus, as a symplectic geometer, there are actually symplectic manifolds with this cohomological condition, which are very, very far from being algebrogeometric Fano varieties. And so, you know, none of the classical techniques of mirror symmetry, will actually apply to them. Of course, whether other techniques apply is also a question. Okay, so from now on, this is joint work in progress with Dan Pomigliano. Maybe more correctly to say is that maybe Dan's work in progress with me looking on helplessly. So this exponential type conjecture, including the quasi-unipotent monodromy part, I would like to prove it for all m. You need some geometry. At least you need an anticanonical divisor, but for technical reasons, which have an anticanonical Lefschetz pencil.
Sorry, Paul.
Yes.
In your setup, in your sort of mirror setup there, what would have changed if you hadn't assumed the anti-canonical divisor in M was smooth.
Oh, if I don't assume the anti-canonical divisor in M is smooth, then the mirror superpotential is not proper. Okay, and I'm not saying that it cannot be done, but you know the Gauss-Manin connection in the non-copper case, there's a bunch of additional complications which I was very happy to avoid. Okay, which have an anti-canonical Lefschetz pencil, which means a pencil of hypersurface representing the first Chern class, and so far we reduce this to a really. I think we have essentially a proof, but I'm not going to announce it here. The purely Floer theoretic statement, which is a strengthening. So there's an internal statement about Floer theory. The work of Bormann and Sheridan and Rogunesh. I will refer to maybe as BSE. And I will explain in a second what it is. But so they proved a certain statement, and we need a significantly stronger form of the same statement. And being a lazy person, so far I've just been leaning back and waiting for them to do it, because it seems they're quite close. But that is a statement that has nothing. Well, if that turns out to be wrong, then we're in deep shit. But it's not really intimately connected to the problem as such. And so rather than obviously explaining to you the whole proof in the last 10 minutes of my talk, I will explain to you how the various ingredients that we've used before actually get replaced by more abstract ones, which do not require passing to the mirror. Okay, so first one thing here, this was a basic object. Okay, and even though this may look a little bit strange because of the absence of the Q inverse, it is key that this object be involved, because this is the one that's actually a holonomic D module that we apply Malgrange's theorem to. So, and what will we get replaced? So this gets replaced. A Q deformation. Oh, you're not going to enjoy this. So this is your smooth anticanonical divisor. And this one here is, this is S1 equivariant symplectic cohomology of this non-compact manifold, which is a very well-known symplectic invariant. It's an invariant of the complement, but in the case where this is a complement and acquires a compactification, there is a one parameter formal deformation of this, which is exactly as of this shape with this parameter Q. Okay, the parameter Q measure, this is all this is a Floer theory thing. It concerns, holomorphic maps in this complement and minus D. And then the deformation, you consider holomorphic maps that after all do intersect D, and the power of Q keeps track of how often they intersect D. So it's not rocket science, okay? And so this comes with this Q deformation, also comes with an operator that differentiates D by DQ. So it is a mild variant of a D module. So it's mild variant because in this situation, there's the S1 equivariant parameter U, so you're in a slightly non-traditional world. And so what BSV relates this, the quantum cohomology of N. Okay, so they proved, actually, they looked at the non-S1 equivariant version, and they proved that this deformed thing actually computes the quantum cohomology of M. It was the ordinary cohomology of M. But what we need is, we need this to be true equivariantly, and we need it to be compatible. We need this nabla Q operator here to be to give you the quantum connection over here. That is this thing that I said, this is this purely Floer theoretic statement that we need. if you look at those things that are supposed to correspond to each other, you know, they look very similar and it looks like they like each other. Philosophically, they're constructed exactly along parallel lines. But of course, that doesn't actually prove anything. So this is our replacement for this. And then you pass to Q inverse and so on, and you do various other versions of it as you like. So far, this took place in the world of, you know, essentially Gromov-Witten theory. So we have not actually we have not added anything dramatic to this. But you cannot actually hope to approach this conjecture just within the world of Gromov-Witten theory. Otherwise, I think somebody else would already have done it. Well, I hope you can't approach this. Okay, so now there's another equivalent picture. An equivalent picture of this thing here, E plus, uses the periodic cyclic homology of a Q deformation of the Bragg-Fukaya category. So now I pass to this was what's called a closed open string formalism or open closed string formalism. I pass to the categorical side, and this thing here, the Bragg-Fukaya, so the Bragg-Fukaya category of M minus D is what replaces the space X on which this W lives, and the Q deformation is what replaces this actual W, the superpotential W. So if I was using mirror symmetry, this would be equivalent to the previous picture, but that I don't really care about. Okay, so now there's a purely algebraic interlude. Which is that if you have something like A, let's say it's a, well, I have to say the word at some point. So, you know, you have a, very much like Ken just talked, you have an A infinity category originally, maybe over the complex numbers, and then you have a formal deformation, but where the deformation parameter, say Q, is of degree 0, okay? So I should say that maybe for intuition, is that the first order deformation class, usually the deformation class is a class in degree 2, functional homology. In this case here, it is of, yes.
You mean to write degree 0?
No, degree 2.
You just said degree 0.
No, the deformation class has degree 0. So usually the deformation class has degree 2, but in case where the parameter has degree 2, the deformation class is degree 0. And you can think of this thing here as a function, an element of HH0. This is actually a W, even though it's only the leading order term of W. So there is a, well, maybe Kosul, sorry, everything's called Kosul duality has been generalized to that extent that the word doesn't actually mean anything. Okay, so let's say it like this. At the moment, we prove this under some technical assumptions, but I think it's true in general. So there's a quasi-isomorphic one, which is actually linear over C double bracket T, and the deformation has only one term. which is turning on what's called a curvature term, which is Q times T. Okay, so T is an element in the center of this thing. It's linear over T, and you essentially, this is now your superpotential. It's just given, it's linear over T. So in particular, what am I using this for? So okay, so now you're associated to this one here. It's linear over CT. So you can say, you can take a family of fibers where T is set to some constant. And this gives you a family of categories. It's like the family of fibers of a Landau-Ginzburg model. Okay. And what I'm not going to write down here is that, Dan proved an amazing theorem, which explains how the Gauss-Manin connection on the family of the fibers is the Fourier-Laplace transform of the natural connection d by dq on the q-deformed periodic cyclic homology of the original thing. Okay, so that gives us the required Fourier-Laplace transform. And the last step, I am being very breezy here because there's issues of smoothness and so on. Each of which deserves a little chapter here. But the last step here is not ours, which is the monodromy theorem. So if you remember, I used the classical monodromy theorem as the linchpin of the original argument. So the monodromy theorem for families of smooth and proper. Proper is not a problem for us in this situation. Smoothness needs some consideration. Infinity categories due to. So it says that the non-commutative analog of the Gauss-Manin connection, Getzler-Gauss-Manin connection, has regular singularities, quasi-unipotent monodromy, and it is due to Petrov, Weintraub, and that would be the end of the argument. So the open piece at the moment is this Bormann, Sheridan, Varol-Güneş. As a closing remark, so this is, I'm not really willing to announce this as a theorem, but in the course of working on this, the proof has simplified enormously. So originally it involved taking this family of categories and extending it over infinity and proving smoothness by formal deformation away from infinity, and a lot of wonderful work by Twain. I am slightly worried that we are still in the overkill category here. And why am I slightly worried here? So this is a black box thing, right? So this black box thing is, there is a proof of the monodromy theorem in ordinary algebraic geometry due to cats using a sort of result of Turitin. And what it does is, well, you assume your thing is first of all defined over, not over the complex numbers, but over the rational numbers. And in fact, you only have to invert finitely many integers. So you can reduce mod p for large p, okay? Which seems a very strange thing to do in the context of connections, but okay. And then a connection in characteristic P has a sort of very non-standard notion of curvature, which is the P curvature. And essentially, if the P curvature is nilpotent, that is the criterion that makes the whole thing run. So if you look at this thing here, so this the things that usually take up a little bit of sort of preliminary homework, lifting things so that they're defined over smaller rings, reducing mod p are unproblematic because all the flow theory structures here are already defined, in fact, over Z. Okay. And so you can reduce the mod p at no cost. So I have not been able to see, maybe just not enough thinking. So you could take this these connections that we get that are defined using Floer theory, and not talk about categories of periodic cyclic homology, but just use these connections, reduce them mod P, and try to think very hard about what the P curvature is. And then if you can prove that it satisfies this kind of a nilpotency condition, then you can prove these regularities quasi-idempotent monodromy without having all of the categorical machinery. Okay. You could say, okay, that's maybe a self-defeating remark to end on. On the other side, as I said, this is only this kind of unramified exponential type is only the very most superficial level of the surface what we're scratching here. Okay, so this, which is because I did formal expansions near Q equals infinity. So beyond the next step, beyond formal expansions, there's a wealth of information classically encoded as Stokes structures. And so the next level is sort of conjectures of Dubrovin about the integrality properties of the Stokes structure associated with the quantum connection. And for those integrality properties, if you want to have any chance whatsoever of making any insights, I strongly believe that the categorical framework will in any case be necessary. So, you might be able to get a temporary reprieve, but, we're just getting started here, to be honest. Thank you very much.
Are there any questions?
Why is the deconcentrated version at only finitely many points?
Say very loud.
The deconcentrated torsion. You said it's singular only at finitely many points. So
Why is it? Well, you can actually. So you mean the symplectic geometry situation? Yeah. You can actually see. As from this work of Bormann, Sheridan, Barrow-Gunesh, it will actually follow if you stare at it for just for a little bit that the singularities of this connection are exactly the eigenvalues of quantum multiplication with the symplectic class. So not only finitely many, but you know exactly.
but that's not open. That's actually.
Nah, it again uses something that's a little bit stronger. But in that case, I believe that if those people fail us, we could probably assemble a proof by ourselves using unlimited, analytic means. So that's not what I'm worried about. So the question was, how do I know that it's got finitely many singular points in this situation from symplectic topology? Well, I'm sorry, I should say that I do know this anyway because it's constructed from a holonomic D module. Okay, but then the proof that it's a holonomic D module actually goes back to quantum multiplication with the first Chern class and actually proves that fact. Any question?
In what sense did you avoid using mirror symmetry in the proof here? It looks like you just sort of have written a proof of mirror symmetry for this Fano map.
Well, at no point have I constructed a mirror, which is an object. Well, it's sort of a tautological interpretation of Konsevich's homological mirror symmetry. At no point did I construct an object of complex geometry, which was actually the mirror. And I don't care if one insists or not. The mirror is sort of tautologically defined as the Fukaya category of this thing.
Any other questions?
How did we get the proper condition here? Because we started only with an anti-canonical device.
Sorry, the question was, how do we know properness?
Yeah.
Is that the question? Okay, so it's actually very sorry. I realized I took this off. I apologize to all the people watching me online. I mean, properness is properness. Relative to it's like fiber-wise properness. Okay, so it's just the fact that the divisor D that I removed is smooth means that when you do symplectic cohomology, you get like a contribution from generators going once around, twice around, 3 times around, and so on. And each of them is of finite dimension. And that's the proof of properness. So this is elementary symplectic geometry. But it would definitely fail if the divisor that you removed was smooth, was singular. So around normal crossings, you get much faster growth than you can bear.
Any other questions? Or if not, let's thank Paul again.